All right, today we are talking about how to factor polynomials. And we've already done this with quadratic polynomials, where we took the expanded form of a quadratic and we rewrote that in a factored form. But now we've said that every polynomial can be written in an expanded form and a factored form. A couple of days ago, maybe last week, we took polynomials in factored form and we rewrote them in expanded form. And that is relatively easy compared to what we're going to do today. Today, we're going to take expanded form polynomials and rewrite them in factored form. And we're not just doing that with quadratic polynomials, but now we're doing that with polynomials with degree 3, degree 4, degree 5, and so on. And people normally consider this to be the more difficult way to do things, right? If you're trying to rewrite it in factored form. But just as a little reminder, the integers is a set of numbers that includes all of your counting numbers, 1, 2, 3, 4, 5, 6, 7, 8. And it includes 0, and it includes all of the negatives of all of the counting numbers. -1, -2, -3, and so on. A rational number is any number that can be represented as a fraction. So like 3/5 is a rational number. But also, if you just have the number -7, or any integer, this is a rational number because you could always just say that's -7/1, right? And so all the integers belong to the set of rational numbers, but the set of rational numbers also includes any fractions that you see. And we also said that there are some real numbers that aren't rational. Like the square root of 2 is not rational. We say that it's irrational. The square root of 36 is rational because that's just an integer. But anytime you have the square root of a number and it's not exactly an integer, the way that square root of 36 is an integer, that is going to be irrational or not rational. And then the last thing is you are also familiar with another irrational number. The number pi is not rational. So if you see pi anywhere, it's another example of an irrational number. And I bring this up and I restate this because those definitions are all included here. This is the big strategy that we are going to use for factoring polynomials. This is called the rational root theorem. And anytime you've got a polynomial with degree 3, degree 4, degree 5, and I ask you to factor this, you'll probably be using the rational root theorem every time. This says, suppose capital P is any polynomial whose expanded form has only integer coefficients. That's important. If you're going to use this rational root theorem, your polynomial has to have coefficients that are only integers. You can't have fractions, you can't have irrational numbers, and so on. If that's the case, then all of the rational number roots have to be included in this list. And we're going to make a list that looks like plus or minus factors of the constant term divided by factors of the leading coefficient. And you've got to memorize this for your next test. That means if your polynomial has any roots that are rational number roots, then they'll show up in that list when you make that list. But again, there's 3 bullet points down here because there's 3 things I want you to remember about the rational root theorem. Before you try to apply the rational root theorem, make sure that your polynomial has only integer coefficients. Number 2, you should realize this rational root theorem, it's not going to tell you what the roots are. It's only going to give you a list of possibilities. But it's most often the case where you'll have like a degree 3 polynomial, and if it's degree 3, you know that there's only up to 3 distinct roots, right? But you might have a list of like 8 possibilities. So not every one on the list is going to be one of the roots. This is just a list of possibilities. And then the third bullet point says, that list that you make is only going to include rational numbers. If your polynomial has some roots that are irrational, or if your polynomial has some roots that are not real numbers, maybe they're imaginary numbers, then they're not going to show up on your list, even though it's a root of your polynomial. Okay? It might be more clear here in a second whenever we do some examples. So here's an example. Use the rational root theorem to generate a list of possible roots for the following polynomial. What is my constant term here? Negative 15. And then what is my leading coefficient in this case? Yeah, it's just the number 2. So what my rational root theorem says is that I'm going to make a list of possible roots that looks like plus or minus factors of my constant term, which is negative 15, divided by factors of my leading coefficient, which is 2. Now, the factors of 15 are 1 times 15 and 5 times 3. So that's the list of all of the factors of my constant term. 1, 3, 5, 15. The factors of 2 are just 1 times 2. And so that's the list of numbers I get in my denominator. And so we are almost done. This question only asked us to create a list of possibilities. And to make this list, I'm going to consider all of the possible combinations of my 4 choices in the numerator and the 2 choices in my denominator. So, in other words, one of the possibilities will be 1 divided by 1. Another would be 3 divided by 1, 5 divided by 1, and 15 divided by 1. But I also have to consider 1 divided by 2, 3 divided by 2, 5 divided by 2, and 15 divided by 2. So altogether, there are going to be 16 possibilities, because we get the positive numbers on the list and the negative numbers. And 16 is a lot of possibilities. So it's not going to be very easy to narrow this list down. But at least 16 is a place to start, right? I mean, before writing this list, there's infinitely many possibilities out there for what these roots could be. And at least we narrowed it down to 16. This is all you would have to do in this kind of question. This kind of question just says, use the rational root theorem to generate a list of possible roots. And we did that. This is what I would expect you to do for your answer. in this kind of question. Here in a minute, we're about to not only make a list of possible roots, but we're also going to determine which one of these possibilities is actually a root. And the way you would do this is you would just take one of these at a time, right, like the number 1, and you're going to plug it into your polynomial. And I would write 2 times 1 to the 4th power minus 13 times 1 cubed plus 4 times 1 squared plus 61 times 1 minus 15. And if I plug in x equals 1, that's what it looks like to evaluate my polynomial. And when I evaluate this polynomial at the point x equals 1, this is, I don't know, but it's not 0. I know it's not 0 because 61 is a big number, and so it's going to be some positive number just because of that 61. But this is not 0, and I care about whether or not this is 0. If I take a root and I plug it into my polynomial and I evaluate it, I should get y equals 0, right? In other words, the roots of a polynomial are also the zeros of a polynomial function. You plug in a root, you simplify, you should get 0. If I get something that's not 0, this means one is not a root. Because if this was a root, I should have gotten 0 when I tried to evaluate. And then we go back to my list, and I say, all right, I tried that one, and it was not a root. So I scratch it off the list. And then you can go in any direction. Maybe we try -1 next. Maybe we try +3 next. Maybe you try -5/2 next, right? You just guess using the numbers on your list, plug them into your polynomial, you evaluate it. If you get 0, that's great, you found a root. But if you don't get 0, then you scratch it off. Does that make sense? So that's the idea. That's what I mean by testing these out. We're going to do another one just like that. It says, use the rational root theorem to generate a list of possible roots for the following polynomial. And here's a question. Can I use the rational root theorem on this polynomial?
No.
No, why not?
This is your fractions.
Yeah, thank you. So the rational root theorem says this only works when you have integer coefficients, right? I told you that would be important. You can only use the rational root theorem if you have integer coefficients. And coming back to my example, 19/3 is not an integer. 91/3 is not an integer. So I can't use the rational root theorem. There is a way around this, though. And what we're going to do here, in order to make a list of the possible roots, is I'm going to take this whole polynomial and multiply the whole thing by 3. And if I multiply this by 3, I get 3x to the 4th power minus 19x cubed plus 3x squared plus 91x minus 18. In green, now I have a polynomial that has all integer coefficients. And the other cool thing is that green polynomial has exactly the same roots as the one I started off with. The green polynomial is different from my original polynomial, but it still has the same roots. I'm going to show you a picture of what I mean by that. So let's make up a polynomial. Like this nice red one. Make it a little shorter. And you can see where the roots are because the roots are just the x-intercepts of this curve. So where the red curve passes through the x-axis, I've got a root at x equals -5, x equals 2, and x equals 4. And if I were to take this and multiply by some number, just some constant number, like the number 3, I'm going to get a different polynomial, like the one in blue. But notice I have exactly the same roots. Still at -5, 2, and 4. And so anytime I multiply a polynomial by a constant, I'm not changing the roots at all. Definitely a different polynomial, but it has the same roots. The reason for that is because every point is getting multiplied by this number, only the roots have a y value of 0. And if you multiply 0 by any number, you just get 0 still. So same places have the same roots. And that's what's happening here. If I'm only considering making a list of roots, I can think about a different polynomial with the same roots. And this one has all integer coefficients. So we're good to go. Now, when I try to use the rational root theorem, I need to make a list where I have plus or minus the factors of 18, which are 1 times 18 and 2 times 9 and 3 times 6. Divided by the factors of 3, which are 1 times 3. So I might have a lot of possibilities here. I've got 6 choices in the numerator, 2 choices in the denominator, 2 choices of plus or minus sign. So I might have like 24 possibilities. Let's try it out. I've got 1 divided by 1, 2 divided by 1, 3 over 1, 6 over 1, 9 over 1, 18 over 1. But I also have 1 over 3, 2 over 3, 3 over 3, but that's just the number 1, and I've already put that on my list. I get 6 over 3, but that's just 2, and that's already on my list. I get 9 over 3, but that would be 3, and I already wrote that in my list. And then the last combination is I could have 18 over 3, but that's just 6, and 6 is already on my list. So a bunch of those were redundant, and you don't have to write it down twice. But I also get the negative, so -1, -2, and so on. And I actually only end up with a list of 16 possibilities.
Is it possible that instead of putting like plus or minus, can we do both plus or minus at the beginning?
Yeah, that'd be fine. As long as I know what you're talking about. And that would be it for this question, because this question only asked us to make a list of the possible roots. And that's a good list of the possible roots that you would discover with the rational root theorem. Okay, are there any questions about how to use this rational root theorem for right now? All right. Let's see what else we have. This one says, based on their coefficients, identify which one of these is a polynomial already suitable for the rational root theorem, which ones are not suitable for the rational root theorems, and which ones could be with a little bit of extra work? Is this going to be suitable for rational root? Yes. We already have integer coefficients, so that's good to go. What about this one? No? Could I make this polynomial more suitable just by multiplying by 3? I could get rid of that denominator if I multiply by 3, but why does that still not work?
Square root of 2.
Yeah, I can't fix the square root of 2. Anytime you have an irrational coefficient, like the square root of 2, there's no way to save it, right? You just can't use the rational root theorem. So that's a polynomial, but that you will never use the rational root theorem here because of that irrational number. What about this one? Yeah, it could be. It's not ready for the rational root theorem right now, but if I take this and I multiply times 12, then I would have all integer coefficients. Okay, what about this one? Okay. If I were going to use the rational root theorem, I list the factors of the constant term divided by the factors of the leading coefficient. What's my constant term?
1.
Yeah. There's not a constant term here. So if I tried to use the rational root theorem, I'm just going to get 0. Here's what I would do in this case. For that particular polynomial, I would factor out the greatest common factor. And for that polynomial, the greatest common factor is x. And what I would be left with is x to the 4th minus 4x plus 2. And now, you could definitely use the rational root theorem here, right? Your constant term is 2. So this one, it could be with a little bit of extra work.
I was wondering, can you not just, on the top right one, can you not just square everything? And get rid of?
So you can't square each term individually. You were right to say that if you took, this is a great question, it really is. If I took the whole polynomial and just squared the whole thing, like what if I started with this red polynomial and I made up a new one that is just the same thing squared? My new polynomial in purple actually has the same exact roots as the red one. But taking the whole polynomial and squaring it means you've got to do the big, ugly multiplication box, right? And you have to multiply all of the terms from this polynomial times itself, right? So you'd have the 4/3 x cubed, 4/3 x cubed, minus x squared, and so on. And you would end up getting rid of the square root 2 in some places, but it would also show up again in other places. And you would never quite be able to get rid of the irrational coefficients entirely.
Okay.
It's a great question. Very good question. All right. Moving on to this one, bottom left. Could I use the rational root theorem?
No.
Nope. Again, because of the square root of 3, that's irrational. What about this one? Nope. Because the pi is irrational.
On the one where we just took out the x, the leading coefficient will be 1 for the x4 or x to the 4th.
Yeah, it would be 1.
1, okay.
And so it would be a really short list. It would be that. 1, 2, -1, -2. Yeah. Good questions. I said this before, but I want to show you a little example. The rational root theorem cannot find irrational roots. So if we look at this polynomial, rational root theorem would say, give me plus or minus 1 times 5. Those are the factors of my constant term. Divided by 1, because my leading coefficient is 1. And so this would be a very short list of possibilities. Just be 1 or 5 or -1 or -5. And what that's saying is, if this polynomial has roots that are rational numbers, then they could only be one of those 4 choices. But if I actually wanted to solve for these roots, what I could do is use the quadratic formula, right? R equals -b, of course b is 0 for this particular quadratic function. I'll go ahead and write it down in case you forgot. This will still be relevant in your upcoming test, so make sure you still have it memorized by test time. And it's the square root of b squared minus 4ac divided by 2a. But here, a is 1, b is 0, and c is -5. So that means this is plus or minus the square root of 20 divided by 2. In other words, plus or minus the square root of 5. Those are actually the roots of the polynomial. And the reason they don't show up in my list is because those are irrational numbers. And you only get to find the roots that are rational roots using the rational root theorem. So now we're ready for the main event today. And we're going to be factoring polynomials. I've got a 4-step procedure for factoring polynomials. Step number 1, we're going to multiply and divide by all denominators to make all of the coefficients integers. This time, in my example right here, not all of the coefficients are integers yet. But what I can do is multiply this whole thing times my denominator 2, and that would give me all integer coefficients. But this time, I don't want to change the value of my polynomial. I want to keep it the same. And so in order to keep the same value here, I'm also going to multiply by 1/2. Because 2 times 1/2 is 1. I can multiply by 1 without changing the value. But what that's going to look like in the end is 1/2 times parentheses 2x to the 5th plus 1x to the 4th minus 8x cubed plus 5x squared. That's what I mean when I say multiply and divide by the denominator. I'm multiplying by 2, and I'm kind of dividing by 2. Step number 2 says I need to factor out the greatest common factor. And my greatest common factor for these 4 terms inside the parentheses is
X.
You're close.
X squared.
Yes. X squared is the greatest common factor here. And when I factor out an x squared, I'm going to be left with 2x cubed plus x squared minus 8x plus 5. Like that. That's what I mean by factor out the greatest common factor.
I was gonna ask if we could do that, like, if that was gonna be the first step, but do you do that after you multiply by 2 and then divide by, or divide by 2?
It doesn't matter. You could do that in either order if you wanted to. If you were really passionate about switching the order of steps 1 and 2, that's totally fine. Okay, so now step 3. I have left a cubic polynomial inside the parentheses, and that means I have to use the rational root theorem, right? I can't just use like the quadratic formula because it's not quadratic. And rational root theorem is the only skill we're going to learn in this class for factoring any polynomials of degree 3, 4, 5, or whatever. So using the rational root theorem on this polynomial is going to give me a list of roots that looks like plus or minus factors of my constant, 5, divided by factors of my leading coefficient, which is 2. And so this list is going to be 1 over 1, 5 over 1, 1 over 2, and 5 over 2, as well as negative 1, negative 5, negative half, and negative 5 over 2. Eight possibilities here. And like I said, these are just possible roots. They are not the roots themselves. I can only have up to 3 distinct roots with a cubic, but I've got 8 possibilities. We've got to test these out and see which ones are actually roots. And I could test them out the old-fashioned way, just by plugging them into my polynomial and evaluating the polynomial. Check to see if it's equal to 0. But a slightly faster way of doing things is synthetic substitution. So I'm going to go ahead and do synthetic substitution. In writing the coefficients of my polynomial, I get 2, 1, negative 8, and 5. And what I put inside the box is, what am I trying to evaluate for my polynomial? Should I try 1 or should I try 5, maybe negative 1? What do you want to do first? 1? Okay, so I put a 1 there. Bring down the 2. 2 times 1 is 2, plus 1 is 3, times 1 is 3, plus negative 8 is negative 5, times 1 is negative 5, plus 5 is 0. So if you remember synthetic substitution from last time, that 0 is the value of my polynomial when I plug in x equals 1. And if the polynomial is 0, that means 1 is a root. A 0 here means 1 is a root. And since 1 is a root, that means x minus 1 is a factor. When I go to write this polynomial in factored form, one of the factors is going to look like parentheses x minus 1. Because that's 1 is a root. So let's rewrite this purple polynomial up here. I'm going to rewrite it down below. And this was 1/2 x squared. Now I know one of the factors is x minus 1, and I don't know what's left. Right? Once I take the x minus 1 factor out of that cubic polynomial, I'm going to be left with something that goes inside those parentheses. I just don't know what. And what we're going to put inside of these parentheses right here is going to be this cubic polynomial divided by x minus 1. Okay? And if I want to divide this cubic polynomial divided by x minus 1, I could use polynomial long division, right? But I could also use synthetic division. Synthetic division is a little bit faster, and I'm good to use synthetic division because this denominator is linear, and it's monic, so I'm good to use synthetic division. If I was going to divide this by x minus 1 using synthetic division, what I would do is I would draw a little box, and I would write 2, 1, negative 8, 5 across the top. And in the little box, I would write a positive 1, because in the box, you write the root of the denominator. But I already did it, right? Just a moment ago, I already did synthetic division with 2, 1, negative 8, 5. And in the box, I put the root of my denominator, 1. And so I get the division problem for free. I've already done it. And that means I can go ahead and write the quotient down right here. I write 2x squared plus 3x minus 5. And like I said, I get that for free just from looking at those numbers. This is another really compelling reason to use synthetic substitution instead of just old-fashioned substitution by plugging in the numbers. Because if you use synthetic substitution and you actually find one of the roots, you don't have to go and do a division problem on top of that. You've already done the division problem. And that's kind of neat. Saves you a little time.
So if there's multiple roots, you have to do x minus 1, 2x squared plus 3x minus 5? Like, or is that all together? Or is it just for one root?
That's a great question. That's a great segue into what I was about to say next. We're not completely done factoring this. This isn't in completely factored form. I still need to factor the quadratic part, right? But we already know how to factor a quadratic polynomial. It's going to look like a times x minus r1 times x minus r2 whenever I rewrite that in factored form. Of course, a for this quadratic polynomial is just the number 2. And the only thing I need to know to rewrite this in factored form is what are the roots of this quadratic, right? There's 2 roots. We can always find the roots using the quadratic formula. And the quadratic formula says, negative b over 2a plus or minus the square root of b squared minus 4ac divided by 2a. So this is negative 3/4 plus or minus 7/4. Because this is 9 plus 40, and the square root of 49 is 7. And that means my 2 roots are at negative 3 minus 7, which is negative 10 over 4, which is negative 5 over 2, and at negative 3 plus 7, which is 4 over 4, which is 1. That means x minus 1 is a root, or is a factor, and x plus 5 over 2 is a factor. And if I were only trying to factor the quadratic part, that's what it would look like in factored form. So let's go back and write my final answer. And my final answer here is x squared times x minus 1 squared times x plus 5 over 2. There's an intermediate step that I skipped. I'll show you what I skipped over. I could have written 1/2 x squared times x minus 1 times the quadratic part. And the quadratic part is 2 times x minus 1 times x plus 5 over 2. Yes, the 1/2 times 2 cancels. And then I've got 2 copies of the x minus 1 factor, so I can write x minus 1 squared. And this is your final answer in completely factored form.
So once you find one that's a root, you don't have to see if any other one fits?
That's a great question. So I would say every time you get down to just a quadratic polynomial left, you should just switch and use the quadratic formula to find the last 2 roots. Because if you were to continue to use the rational root theorem, you would have to try out these 8 possibilities, right? 1, 5, half, 5 halves, and so on. And you know, maybe you would try 1 again, and you could find that as your next root, and then you would try 5, and -1, and -5, and half, and -half, and eventually you would find -5 over 2 is your second root. But I feel like the quadratic formula just gets to the punch faster than having to try out a bunch of different things with synthetic substitution. And aside from that, you might have a case where 2 of the roots are irrational numbers, in which case the quadratic formula would tell you what those 2 irrational roots are, but the rational root theorem, none of those numbers are going to work. They're not going to find it. And so the quadratic formula is more reliable in actually getting the last 2 roots every time. But it's a good question. I've got one more example for you today. This example says, find all solutions to this equation. And I've got another little 3-step procedure up here for you. Step number 1, let's move everything to the left side. So looking at this equation and moving everything to the left side means we write -5x to the 4th minus 40x cubed minus 50x squared plus 160x plus 175 equals 0. That's always step 1. So we want to make the right side equal 0. And in step 2, we want to factor the left side. We want to factor this polynomial. So as I'm thinking about factoring it, I think I want all my coefficients to be integers. Well, good news, they're already integers, so I don't have to do anything with that. The next thing is, can I take out a greatest common factor? Yeah, the number 5. All of these coefficients are divisible by 5. And in fact, I really like having a positive leading coefficient. It's kind of just personal preference. So I might go ahead and divide this whole equation by -5. And that would give me x to the power 4 plus 8x cubed plus 10x squared minus 32x minus 35. And 0 on the right-hand side divided by -5 is still 0. And whenever I'm just solving an equation, I don't actually have to keep track of the leading coefficients or anything like that. Right, I don't need to factor out a -5 because all I really care about is how do I solve this equation. And so far, the equation is still balanced. So, step number 3 says, whenever I get done factoring this, the roots of this polynomial are going to be the solutions. So I don't even have to rewrite this in factored form. All I really have to do is find the roots. And this is the point where we go ahead and pull out the old rational root theorem. And I say, I'm going to make a list of possibilities that looks like plus or minus the factors of 35. That's my constant term. So that's 1 times 35 and yeah. 5 times 7 is also 35, so that's my factors of 35. Divided by the factors of the constant, or the leading coefficient, which is just 1. And so I'm going to get 8 possibilities here. And we have to use synthetic substitution to try out some of these possibilities and see what works, what doesn't work. Which one should I try first? 1? Okay. Let's see if 1 is a root. So I bring down the 1. 1 times 1 is 1, plus 8 is 9, times 1 is 9, plus 10 is 19, times 1 is 19. Negative 32 plus 19 is going to give me negative 13. Times 1 is negative 13. And when I add those negatives together, that's not 0. I don't know what it is, but it's not 0. And if it's not 0, that tells me 1 is not a root. And I can go ahead and scratch that off my list. Then we get out our eraser and we scrub some of these numbers off. And we try again. What should I try next? Negative 1? Okay. So 1 times negative 1 is negative 1, plus 8 is 7, times negative 1 is negative 7, plus 10 is 3, times negative 1 is negative 3, plus negative 32 gives me negative 35, times negative 1 is 35, and that gives me a 0. And if I get a 0 down here in the box, that tells me this is a root. And if negative 1 is a root, then one of the factors here is x plus 1. So let's go ahead and rewrite my polynomial as x plus 1 times x cubed plus 7x squared plus 3x minus 35. Now, I'm left with a cubic polynomial. And so with the cubic polynomial, I would want to use the rational root theorem to make a list of possibilities. And I would have as a numerator the factors of 35. And as a denominator, I would just have 1 because that's my leading coefficient. And I actually already did that, right? My list of possibilities has not changed, except I did figure out that 1 is not a root. So let's pick it up from here. What should I try next to determine if it's a root? Oh, and by the way, you do have to change the coefficients now, because I have to use these cubic polynomial coefficients. So it'll be like 1, 7, 3, and negative 35. Sorry, what did you say you want to try next? 5? And I should also say, negative 1 is still on the table. It could be a repeated root, in which case you'd have negative 1 show up twice. So that's a possibility. But let's try 5 next. So bring down the 1. 1 times 5 is 5. Plus 7 is 12. Times 5 is 60. Plus 3 is 63. 63 times 5 is 315. Plus 35 is 280. So that's not a root. And I don't have to worry about 5 anymore.
-1.
Yeah, let's try negative 1 again. It might be a repeated root for all we know.
Oh, yeah, look at the wood.
So bring down the 1. 1 times negative 1 is negative 1. Plus 7 is 6. Times negative 1 is negative 6. Plus 3 is negative 3. Times negative 1 is 3. Plus negative 35 is negative 32. Oof.
Nope.
So it's not a repeated root. It was only a root with multiplicity of 1.
-5.
Okay, that seems like a logical next choice. Let's try negative 5. Bring down the 1. 1 times negative 5 is negative 5. Plus 7 is 2. Times negative 5 is negative 10. Plus 3 is negative 7. Times negative 5 is 35. And voila. That tells me negative 5 is a root. And if negative 5 is a root, that means x plus 5 must be a factor, and the remaining quotient would just be x squared plus 2x minus 7. I got x squared plus 2x minus 7 by looking at these numbers, because it's like we just did synthetic division, right? So we're finally at the point where we have just a quadratic left. And like I said before, if you get to the point where you only have a quadratic left, let's go ahead and just use the quadratic formula to find the last two roots, because that's going to be faster and more reliable, I think. And so for this quadratic, a is 1, b is 2, and c is negative 7. So my quadratic formula tells me the roots are going to be negative b over 2a plus or minus the square root of b squared minus 4 times a times c. So that's negative 1 plus or minus the square root of 4 plus 28.
What do you need? 2? Square root, cancel. Square.
Underneath the square root is actually 2 squared minus 4 times negative 7. So it's 4 plus 28. And 4 plus 28 is 32. You can't just say the square cancels the square root, because you've got to include everything under the square root first. All right, so simplifying this answer might take a little bit of work, but the square root of 32 is the same thing as the square root of 16 times 2. And the square root of 16 is 4. So I can take that out of the square root, and my roots are at negative 1 plus or minus 2 times square root of 2. But those were just the quadratic roots. I have 4 solutions overall to my original equation. The solutions are negative 1, negative 5, negative 1 plus 2 square root of 2, and lastly, negative 1 minus 2 square root of 2.